Hello students, very good afternoon. My name is Ravi Ranjan Kumar and I welcome you to this session. This last 2 days of this week, we are going to cover uh, units and dimension, measurement and error analysis, and we will also talk about vernier caliper and screw gauge. Okay, so here without losing any further time, let's start today's discussion. In today's class, we will be talking about error analysis and units and measurements. So let me share my screen with you guys. So I hope I am visible to you guys. Some connection problem was there earlier. So let me share my screen again with you. So I hope now it's visible. Okay, so here we go. So measurement and error analysis. So first of all, we will start with units and dimension. Okay, so let's first talk about units. As you understand, the measurement of any physical quantity is expressed in multiples of a standard basis, which is also widely accepted. That is called a unit. Okay, and units basically you can divide it into three categories. Okay, units will be either fundamental units, or it will be derived units, or it will be a supplementary units. We will be talking about each of them one by one. So let's first talk about fundamental units. Okay, so in SI system, seven quantities which are independent of each other have been identified and termed as fundamental physical quantity. So basically these are seven physical quantity. You should realize that these are independent of each other, independent of each other. They have been identified. Okay, and remaining other physical quantities you can derive with the help of seven fundamental physical quantities that you can derive uh, from fundamental units, you can say. And apart from that, like two other supplementary units has been identified, okay, and inducted in unit system. And these units are basically are ratios. Like one of them is a plane angle, and its unit, you understand, is radian. And the another is again a ratio, that is a solid angle. Okay, and its unit is steradian. Okay, so these are supplementary units. Like although these two physical quantities are dimensionless because they are ratios, but we assign unit to them. Okay, the unit of plane angle is radian, and unit of solid angle we say it as steradian. Okay, so first we will be discussing about the fundamental units. Let's have the list of those seven fundamental physical quantities and their units. Okay, so seven fundamental quantities or physical quantities, you can say. So I will draw a table. So in first column I will write physical quantity, and in the second column their corresponding units, and in third column we will write their symbols. Okay, and then we will use a fourth column where I will be putting dimensional symbol. Okay, so physical quantity, the first one, the first fundamental physical quantity is mass. Okay, and its unit is kilogram. SI unit I am writing. Okay, and symbol of kilogram is kg, and dimensional symbol would be m. Okay, and then we will be having length, and its meter is its unit, and its symbol is M, and dimensional symbol is L. And third fundamental physical quantity is time, and this is second. Okay, and its symbol is S, and its dimensional symbol is T. And then we have current, or electric current, you can say electric current, and its SI unit is ampere. Okay, its symbol is A, and its dimensional symbol, we will use it as capital A only. And then we have, say, thermodynamical temperature. Its unit, SI unit is Kelvin. Okay, and symbol is K, and its dimensional symbol will be K. And apart from that, there is amount of substance, you can say, and its unit is mole. Symbol is MOL, and its dimensional symbol is MOL again. And there is one another physical quantity which is beyond the scope of our syllabus, luminous intensity, and that is something related to photometry, and that is not intensity, please understand. That is a different physical quantity, luminous intensity. That is one of the seven fundamental physical quantity, and its unit is candela, and its symbol is CD, and its dimensional symbol is CD. So you realize the first three fundamental physical quantity, with the help of these three, we will be able to derive all the units which are related to, say, mechanics. And when we introduce electrodynamics, we will be using this electric current also. Temperature and amount of substance will be introduced in thermodynamics, etc. Okay, so luminous intensity, basically this fundamental physical quantity we will not be using in our syllabus. So these are seven fundamental physical quantity and their corresponding units. So now let's talk about derived physical quantities. Okay, so for example, any physical quantity which we are having, let's also take some example. Physical quantity is given to us. See, so we want its derivation first. Its derivation means its relationship with the fundamental physical quantity, derivation. And then we must be able to write its dimension, and then we must be able to write its unit. So let's take some example over here. Let's say, for example, force. So if we want to write the dimension or derive the dimension of force and a unit of force here in terms of fundamental physical quantity, we must have some relationship. For example, F is equal to MA, we know, right? And A also is a derived physical quantity. So anyways, so when we will be writing its dimension, dimension of F would be same as dimension of mass and dimension of acceleration. So dimension of mass is M, and dimension of acceleration would be nothing but LT minus 2. So dimension of force can be derived as MLT minus 2. And similarly, you can write unit also. Okay, so unit of mass is kg, and unit of acceleration is nothing but meter per second square. And see, one name we introduce for this kg, meter per second square, and that you all are aware is nothing but Newton. Similarly, we can have other example. For example, work, W is equal to Fs would be one of the relationship defining it. Okay, so like its dimension would be dimension of F into dimension of S. So dimension of work, you can write it as like ml square into t minus 2, and its unit you can write it as simply unit of F and unit of S, that is Newton meter, and that is known as joules also. For example, power, if we take, okay, so power is defined by work done per unit time, etc. So its dimension would be definitely dimension of work upon dimension of time. So you can write it as ml square t to the power minus 3, etc. And its unit, you must realize, the unit of work is joule, and unit of time is nothing but second, and joule per second is known as Pascal, etc. So like uh, every physical quantity or every unit except the seven fundamental physical quantity can be said as derived physical quantity. So you can have them, you can have their dimension, you can have their units. Okay, so let's take one other simple example. Let's say, for example, we are required to find unit and dimension of say universal gravitational constant g. So we must find out a relationship which includes this g. So F is equal to g m1 m2 by r square, we know. So that is obvious that g, the dimension of g would be same as the dimension of f r square upon m1 m2, right? So this would be same. Okay, and you should realize dimension of f is nothing but mlt minus 2. Dimension of r square would be nothing but l square, and here the dimension of m1 m2 would be nothing but m square over here. So when we will be combining all these, so g can be represented as, that would be m to the power minus 1, l to the power 3, t to the power minus 2. And obviously the SI unit of g will be same as, like, unit of force would be Newton, unit of r square would be meter square, and unit of m1 m2 would be nothing but kg square. So Newton meter square per kg square. Also, let's talk about one very simple thing. For example, conversion of units. Okay, say you understand, like, when we talk about force, one simple example I am talking about, its CGS unit is dyne. Okay, and its SI unit is Newton, and we wish to find out, like, 1 Newton is equal to how many dynes. So what we got to do for this? So for example, 1 Newton we have learned is nothing but 1 kg meter per second square, right? So we can write like 1 kg, we can convert it into, like, this is fundamental units, so we can convert it into CGS system, and unit of mass in CGS system, you know, is gram. So kg we must convert it into gram, so that is going to be 10 to the power minus 3 grams over here. And similarly, the unit of length, that is meter, in CGS unit system is centimeter. So 1 meter, I should convert it into centimeter. So that would be 10 to the power minus 2 centimeter over here. And the unit of time is second in both CGS unit system and SI unit system. So this is going to be S square. So you have realized that it is nothing but 10 to the power minus 5 grams centimeter per second square, and gram per centimeter square is nothing but a dyne. Okay, so that is nothing but 10 to the power minus 5 dyne. So you can have conversion of units between different unit system. One another type of question that is asked is, um, say, for example, 7 independent fundamental physical quantity has been chosen, okay, in a certain unit system, SI unit system. In some other unit system, you can choose some, like, you can assign the fundamental physical quantity to be something else. Okay, so in that case, like, for example, um, mass or length or time could be represented in terms of the fundamental quantities that has been defined in that unit system. So let's take that kind of examples. For example, question is, if velocity, say v, and force, say F, and time, say t, these are, let's say, their corresponding dimensional symbol, are chosen to be fundamental quantities. Okay, so we have to express dimension of mass, say mass, in terms of V, F, and T. So what we are going to do? So say like dimension of mass, we want to express in terms of velocity, force, and time. So it would be something like V to the power A, and F to the power B, and T to the power C. Okay. So you should realize, like dimension of mass, you can write it as m. So that would be m to the power 1, L to the power 0, T to the power 0, etc. You can write. And dimension of V, you can write it as LT minus 1. Okay. And to the power A, dimension of F, you can write it as MLT minus 2 to the power B. And dimension of T, you can write simply T to the power C. Okay, so when you will be combining that, you will be getting m to the power b into L to the power a plus b, and t to the power here, that would be minus a minus 2b plus c over here. Okay, and that you can compare with m to the power 1, L to the power 0, t to the power 0 over here. So exponents, when you will be comparing, so you can see the exponent of m is b, and here it is 1. So b is definitely equal to 1. And exponent of L, if you compare, so you realize that a plus b is nothing but equal to 0. And the value of b we already know. So from here, we get the value of a as minus 1. And comparing the exponent of t, we get minus a minus 2b plus c is equal to 0. And we already know the value of a and b over here. So solving that, you will be able to get the value of c as 1. So knowing these, the value of a, b, and c, like the dimension of m can be represented as v to the power a, and a is nothing but minus 1, and f to the power b, and b is nothing but 1, and t to the power c, and c is nothing but 1. So that would be the dimension of mass. Okay, in some other unit system where we have fundamental units as v, f, and t. Okay, so that was one of the ideas. And the another thing you must realize is say dimension in case of, say, trigonometric function, right? Say, for example, you have some trigonometric function y is equal to a sine kx. Okay, so you should first of all realize, like for example, this quantity kx over here. So kx generally, like when you are taking sine, okay, you take sine of a plane angle. So this quantity is nothing but a plane angle, and plane angle, you should realize, although it has its unit, we have unit is radian, but it is a ratio. Like plane angle is a ratio, so it's dimensionless. Please understand, that is dimensionless. So what we can say about kx over here, that is a unit is radian and it's dimensionless. So from that, like if x is has a dimension of length, okay, so unit and dimension of k we can find out. So obviously kx is dimensionless. Okay, so we can say this is dimension less. So clearly you can say the dimension of k would be same as dimension of 1 by x over here, or you can say that would be simply L to the power minus 1. And what would be its unit? So unit of k would be same as the unit of x inverse, and x inverse is nothing but uh, that you can say the kx has unit radian. So it would be unit of k would be nothing but radian per meter over here. So that you can say simply. Okay, so that is what we can say about this kx term. And apart from that, you should also realize, like this sine kx term, okay, this sine kx term is nothing but a trigonometric ratio. So ratio, it will neither have unit, so that would be unitless, and dimensionless as well. Okay, so looking at that, you can clearly say that if this quantity is unitless and dimensionless, so y would be having same dimension as a. If whatever the dimension is of y, same would be the dimension of a, and whatever is the unit of y, same would be the dimension of same would be the unit of a over here. So that is one thing. And also, if you represent it as in inverse trigonometric form, okay, let's say for example, you can represent it as kx is equal to sine inverse y by a, and you should realize the same thing which you realized earlier. So basically kx, this would be a plane angle, that is a plane angle, so that would be unit would be its radian, and it would be dimensionless also. And this, you should realize, this quantity here is a ratio. Okay, and this quantity would be simply a plane angle, etc., that you can figure out. So that is one thing you need to notice. Okay, and another thing let me discuss over here is dimension in case of exponential function. Dimension in case of exponential and say logarithmic function. So if we have something like a is equal to a naught into e to the power minus kt kind of thing. Okay, so first of all, you should realize that this quantity, this is the exponent over here. So first of all, this quantity kt would be unitless and dimensionless. So being said that, you can say the dimension of k would be same as dimension of 1 by t over here, and unit of k would be same as unit of 1 by t over here. And also, you should realize that this quantity e to the power minus kt would be also unitless and dimensionless. So when we have represented a is equal to a naught into e to the power minus kt, since that quantity is unitless and dimensionless, you can say the dimension of a and a naught would be same, and unit will be same as well. Alternatively, this function you can represent it like kt is equal to ln a naught upon a. Okay, so when we have represented it like this, so you should realize that a naught by a would be some number, dimensionless quantity. So you can say that a and a naught would be having same dimension. And this whole thing would be a dimensionless physical quantity. So kt would be a dimensionless physical quantity. So you can say the dimension of k would be same as 1 by t. So these are few important things. Okay. Another important thing about units and dimension, let me tell you, is say dimension of derivative. Okay, dimension of derivative. For example, dy by dx, its dimension we want to find out. Okay, so its dimension we want to find out. So you should realize, like, dy by dx is nothing but delta y by delta x only, delta x tending to 0, so that these will be having same dimension. And you should realize this delta y, that is change in y, so basically it will be having same dimension as y, and delta x would be having same dimension as x. So you understand, dy by dx would be having same dimension as y by x, and whatever physical quantity y is and x is, you can find out the dimension of this derivative over here. Like some higher order derivative, let's try to find out. So say dimension of d2y upon dx square you want to find out. So you should realize that is nothing but d of dy by dx by dx over here. This you understand from the definition of double derivative. So you should realize, so numerator is change in dy by dx, you should realize. So it would be having same dimension as dy by dx. Okay, and it would be having same dimension as dx over here. And we have already said that dimension of dy by dx would be same as y by x, so it will be having y by x as dimension, and dimension of dx is definitely going to be x. So you should realize this would be y upon x square over here. That would be its dimension. And similarly, you can write, for example, dny to the power 2 upon dx to the power n, dxn you can say. And what would be its dimension? With the help of similar logic, you will be able to simply say it would be y upon x to the power n, same as dimension of y upon x to the power n. So that is the dimension of derivative. Okay. And let's say now also look at dimension of integral. Say we have a function, say fx dx. Okay, fx dx. Fx could be any function of x, and its integral is gx. So you should realize, first of all, what would be the dimension of fx dx over here. So you should realize the dimension of fx we can find out, okay, depending upon what is this function, and dimension of x would dx would be simply x. So that you should realize, okay. And you should also realize that would be same as dimension of gx over here, right? One example, one simple example we can take. Let's say, for example, we have a function a, integral of dx upon some a square minus x square is equal to some v square, and let's say v is a speed, okay, and x is some distance. Okay, so we wish to find out the dimension of a. So let's first try to find out the dimension of this quantity over it. So what would be the dimension of this quantity? So let me write it over here. Dimension of dx upon a root under a square minus x square, and integral. Its dimension we wish to find out. So you should realize its dimension would be same as dx upon root under a square minus x square. And you should realize the dimension of dx would be same as x, and dimension of a square minus x square would be same as dimension of x square over here. Okay, and dimension of x square root under would be same as dimension of x over here. So that you understand, like this quantity here is dimensionless. So that clearly gives the dimension of a would be same as dimension of v square. That you can say that would be lt minus 1 whole square, or you can say l square t to the power minus 2, right? So that is one thing. Another important thing about the units and dimension is one simple principle. Okay, that is principle of dimensional homogeneity. Okay, say for example, only those physical quantities can be added, subtracted, or compared, okay, which are dimensionally same. Like for example, let's say we have a relationship, for example, alpha upon t square is equal to f into v plus beta upon x square. And in this, let's say t is time, f is force, v is velocity, and x is distance. And when we are writing this relationship, and we are assuming this relationship to be dimensionally correct, so the meaning of that thing is, now you should realize, first of all, here, like we are adding these two terms. So you should realize, and adding these two terms and comparing it with this term over here. So clearly that dimension of alpha by t square would be same as dimension of fv would be same as dimension of beta upon x square. So knowing this, you can find out the dimension of alpha and beta over here. For example, dimension of alpha over here would be same as dimension of fv into t square, right? Dimension of fv into t square. So you can say dimension of f is nothing but mlt minus 2, and dimension of v is nothing but lt minus 1, and dimension of t square is nothing but t square over here. So when you will be combining, what you will be getting over here is ml square t to the power minus 1. That is how you can get the dimension of alpha, and dimension of beta similarly you can get. That would be same as dimension of f beta would be dimension of fv into dimension of x square. And when you will be substituting these values, so you will be getting ml to the power 4 to t to the power minus 3, etc. So that is one important thing, principle of dimensional homogeneity. And you can use dimensional analysis to derive a new relationship also. Let's say deriving a new relationship. Okay, let's say for example, if we know that certain physical quantity x depends on other physical quantities, say a, b, and c, then we can always represent x in terms of a, b, and c. Let's say that would be directly proportional to a to the power a and b to the power b and c to the power c, etc. And say there would be some proportionality constant k. Okay, where k I am assuming it to be unitless and dimensionless. Okay, so like we wish to find out the values of a, b, and c, etc. So just by comparing the exponents of dimension, okay, we will be able to do that. For example, one example I am taking here, let's say time period of a simple pendulum depends upon the mass of the bob and the length of the string and the gravitational acceleration. So let's represent it as m to the power a, l to the power b, and g to the power c. And let's introduce some dimensionless physical constant coefficient here, that would be k. And we wish to find out like what would be the value of a, b, and c, so we can compare the dimension. So dimension of t would be same as dimension of m to the power a, l to the power b, and g to the power c over here. Okay, so dimension of t we can write it as m to the power 0, l to the power 0, t to the power 1. And dimension of m we can write m simply m to the power a and l to the power b. And g is basically gravitational acceleration, so it will be having same dimension as acceleration, which is lt minus 2 to the power c. So when we will be combining each and every term, so m to the power a we will be getting an l to the power b plus c, and t to the power minus 2c we will be getting over here. And we can compare it with m0, l0, t1, right? Okay, so comparing the exponent, you will be able to get three equations over here. So first equation is, for example, a is equal to 0 by comparing the exponents of m. When comparing the exponent of l, we will be getting b plus c is equal to 0. And comparing the exponent of t, we will be getting minus 2c is equal to 1. So solving these three equation, you will be like a is equal to 0 we already know, and c is equal to minus 1 by 2, and b from this equation would be nothing but half over here. So you can write t is equal to some k into root L by G over here. To find out the value of K, you have to apply other methods. So these were a few things about units and dimension you need to understand properly, and you need to have it in your mind always. Okay. So now let's now talk about error in measurement. Okay. Error in measurement. As we have understood already that the measurement of a certain physical quantities involves the comparison with a known basis, that is we know it them as units. Okay, so you should understand that the result of every measurement by any measuring instrument contains some uncertainty. Okay, and this uncertainty is called error. Okay, and every calculated quantity which are based on measured values also has an error. Okay, so whenever we are measuring any physical quantity using any measurement instrument, okay, two things we need to look into. One is the accuracy of measurement, and the another is precision of the measurement. So let's try to understand about these two terms, accuracy and precision. These are important terms whenever we are measuring a physical quantity. So accuracy of measurement is a measure of how close the measured value is from actual value. Okay, and the precision is basically the resolution, or you can say limit, resolution or limit of the quantity of physical quantity which has been measured. Okay, let's try to understand the difference between these two quantities. Let's say two students are measuring some length of a say pen, and the pen's length actual value is 12.3475 centimeters, something like that. Somehow we know its true value, let's say given by the manufacturer. Okay, and student one measured it to be, like for example, his measurement was say 12 point say 3. Okay, and student 2, when he measured it to be 12.1731, something like that. So now you see, like when you will look at the measurement of student 1, that is 12.3, which is closer to the actual value, okay, in comparison to this one. So this is accurate, more accurate, rather you say more accurate, but less precise. Why it is less precise? This one is less accurate, but more precise. uh, Looking at the precision over here, you can see like the uh, report, this report of reading, or this reading over here has greater number of figures. Okay, like we will later learn that it is significant figures. So student 2 has reported his measurement in more significant figures. So basically he must be using some sophisticated measuring instrument, having a higher, smaller least count over here. Okay, having higher precision. So that is why his measurement is more precise. But you can see this value is having greater difference from the actual value in comparison to this one. So that is why this is less accurate, but definitely it is more precise. Precision will depend upon the resolution or limit of the quantity over here. Like for example, in how many significant figures the reading has been reported. Okay, so these are two things. Okay, so every measurement has some error associated with it, and let's try to understand what would be the type of errors. So errors can be broadly divided into two categories. Okay, the first one is known as systematic errors. Okay, and the second one is known as random errors. Okay, so systematic error, you should realize, is first of all unidirectional. Okay, that is tend to be either one direction, either it would be positive or it would be negative. So if we are having a systematic error, like in some cases, like some systematic error would be always positive, some systematic error would be always negative. So that is unidirectional, whereas the random error will be having one proper direction. So let's first talk about systematic error first, then we will talk about random errors. So unidirectional, that would be systematic error would be unidirectional, and its sources, how do we get these systematic errors? So the first source is, for example, instrumental error. Instrumental error we can have, for example, imperfect design, or you can have some zero error, etc. So if we are having imperfect design of a measuring instrument, you should understand, or wrong calibration, you can understand, then we will, while measuring from that instrument over instrument, any physical quantity will be having that much error present always, which is due to the instrumental error. And we will be having, we can have positive zero error, we can have negative zero error. So if we are having a positive zero error associated with instrument, so we will always be getting a positive error in the measurement. And let's have another reason for that. Another reason for a systematic error can be imperfection in let's say measurement technique, let's say, and that will vary from person to person. Okay, that is kind of personal error, that is due to individual bias, you can say. For example, parallax, like if you have a habit of like keeping your head a little above while looking at the level, so you will always be having some parallax. Okay, and that will be unidirectional. So these are some example of systematic errors. So now let's talk about random error a little bit. And you should understand, as the name suggests, random error that occurs irregularly. Okay, so it occurs irregularly, and that is random with respect to sign. Okay, so like it could be sometimes same person is measuring and he might get some positive random error, sometime he might get negative random error. So let's learn about its source also. So the source of random error, the first one is the random and unpredictable fluctuation of experimental condition. For example, temperature might be fluctuating, or the voltage if we are doing some electrical experiment. Okay, so voltage etc might be fluctuating, and you must understand, like, the reading will change due to these small fluctuations, you should realize, and we don't have any control over it. And these are basically random errors. The second source of random error you can see due to personal unbiased error. Unbiased error means if same person is measuring same physical quantity, it is highly unlikely that every time he will be measuring, he will be getting the same reading. So that will be due to personal unbiased error. That is not due to any imperfect measuring technique or personal error. That is unbiased error, you should realize. Okay, so this personal unbiased error can be like minimized, you can say. Random error cannot be removed, only it can be minimized. So one important thing about the random errors can be minimized, okay, by taking measurement several times. Okay, that is by increasing the number of measurement, you can say. When you increase the number of measurement, basically you are averaging that unbiased error, or averaging any fluctuation in experimental condition etc. Okay, so you must understand, like, systematic error can be minimized also. Okay, and random errors can be minimized also. Okay, and systematic error can be taken care of, like, for example, by taking care of the instrumental error. For example, you understand, like, this instrument has zero error, so at the end of the measurement, before providing the reading, you take care of this zero error. Or you can improve your measurement technique, and thus you can minimize the systematic errors also. How do you minimize the random errors? By simply the uh, increasing the number of measurements. Okay, so that is one thing. And now let's understand about a few important terms related to measurement. And one thing you need to understand something is about least count. Least count I have used already, like this term I have used already several times. So basically, least count of a measuring instrument is nothing but the minimum possible value. Okay, minimum possible value that can be identified, or you can say measured, okay, using a given instrument. Okay, so every measurement instrument have some least count associated with it, and that is nothing but the minimum possible value that can be measured with the help of that measuring instrument. For example, everybody has seen the meter scale, and the smallest division in the meter scale is nothing but 1 millimeter. So least count of a meter scale will be 1 millimeter, because that is the minimum possible value that can be measured using that meter scale. And you should realize a few important points regarding the least count. So instruments having a smaller least count have higher precision. So you can say smaller least count means higher precision. Okay, smaller least count will simply mean that you will be able to report your reading to a greater resolution. Okay, so that will be a higher precision, you can say, that will be having higher precision. And also maximum random error. You should also realize that maximum random error uh, in a measurement will be equal to least count of instrument. You should realize. Let me explain that fact to you. Let's say, for example, okay, you are measuring some length, and you are say using meter scale. So when you are using meter scale, and let's say you have measured some length to be equal to 12.3 centimeter. Okay, you cannot say something like 12.351, etc., because that would be overstatement. You cannot measure to this much resolution using a meter scale, so that would be an overstatement. You must never do these kind of things in an experiment. Okay, so 12.3 centimeter you have got. It does not mean that you have exactly, your reading exactly is 12.3 centimeters, since the least count of meter scale is 0.1 centimeter. So like it could be, for example, 12.28 or 12.32, etc., anything it could be. So basically it would be like 12.3 plus minus, you can say, that would be 0.1, something like that. And that is nothing but the least count of, okay, this measuring instrument, which here is a meter scale, and that is the maximum possible random error over here. So it is always good if you are doing the measurement only once. Okay, you should write it like that, is the maximum possible error associated with this measurement. Okay, so that clearly defines, okay, like with how much precision you are doing this measurement over here. Another thing you need to understand is about zero error. Okay, like some instruments have some zero error. Like for example, your wristwatch might have some zero error. For example, it may be 5 minute fast or 5 minutes slow, something like that. Okay, so that kind of error is known as zero error. Means when it is supposed to read zero, it is reading something else. Okay, and that something else is nothing but zero error. You realize, like for example, if your watch is reading like 0005 hours at 000 hours, okay, that means it has positive zero error of 5 minutes. Okay, so zero error is nothing but, okay, measured value minus actual value. That is how you can find out the zero error associated with your instrument. Okay, so if you know some actual value, and at that actual value, if you are doing the measurement and get it to be measured value, and if there is some difference, it could be either positive or it could be negative. If there is some difference, so that much is the zero error associated with your measurement instrument. Okay, so you should immediately realize that actual value would be nothing but measured value minus zero error. Okay, or alternatively you can write it as measured value plus zero correction over here. That this term is zero correction. Obviously you are understanding that zero correction is nothing but negative of zero error. That means if you are having negative zero, or if you are having positive zero error, you should realize zero correction would be negative. Positive zero error simply means measured value is greater than the actual value. That is when you will be getting positive zero error. So you need to subtract from the measured value to get the actual value, means correction would be negative. Okay, so zero correction is nothing but negative of zero error. So please understand this thing about zero error. Like we will be using this a lot in, say, next class, when we will be talking about vernier caliper and screw gauge, and we will try to find out the zero error associated with vernier caliper and screw gauge, etc. So now let's discuss one another important thing regarding the measurement, and that is significant figures. Okay, and please understand, like whenever we are talking about significant figure is a term associated with the measured value only. So first thing you need to understand is result of measurement should be reported in a way to indicate the precision of measurement. Like for example, okay, like I took the example of meter scale. Let for example 2.3 centimeter you measured, okay, and 12.3 centimeter and 12.3 centimeter least count associated with the meter scale was nothing but a 0.1 centimeter. So basically this is your reading. Okay, you cannot be sure about whether like it is 12.27 or 12.35, etc. You cannot be sure of that. Okay, because see, the least count of the meter scale is only 0.1 centimeter. So the idea here is, when you will be closely looking at this, okay, although you are certain about these two figures 1 and 2, it is definitely 1 and 2, these figures are certain. Okay, when you are reporting your reading to be 12.3 centimeter, you are certain about these two figures, but you are not so certain about this figure 3. That is basically uncertain, you should realize. Because why I am saying that, like because at this place it could be like for example 12.28. So at this place either it can be 2 or it can be 3. So we are not sure about this thing over here. So like if it would have been 12.28, so like it has been rounded off it like this. Okay, so anyway this digit is uncertain. Okay, we cannot say the this is fixed, like it can be 2 or 3 over here. So that is how we count the number of significant figures. So that is number of significant figures, okay, will be same as like all the certain digits in the measurement plus you can say first uncertain digit. uncertain digit. So if you are reporting a reading, okay, you are allowed to have only one uncertain digit and you should round off the other digit. We will talk about rounding off later. So but that is how you count the number of significant figures. And please understand, number of significant figures you only count when you are talking about any measured value. Okay, right? So This is how it is. Okay, like for example, in this, the number of significant figures is 3. Number of significant digit is 3. So let's try to understand a few things about significant figures. And you should realize more the number of significant figures, greater is the precision of measurement, right? So basically, we are using an optical instrument with a smaller least count. So smaller the least count, greater would be the precision, more will be the number of significant figures, you should realize. And the another very important thing you must understand, that changing units does not change the precision of measurement. For example, if you have let's say measured some length, and or measured some mass, and you have got it to be, let's say, 13.8 kg. Okay, and you just wanted to represent it in grams. Okay, so that would be nothing but 1380 grams. So you have done nothing. You have already measured using some instrument, and you are getting 13.8 kg, and now you wanted to represent it in some other unit, say gram. Okay, so just by changing units, you cannot change the precision of measurement, because the measurement depends upon the measuring instruments only, and not on the units. It will depend upon the least count of the measuring instrument. So the idea here is, like whatever is this number of significant figures in 13.8 kg, same would be the number of significant figures in 1380 gram. Okay, and you should realize the number of significant figures clearly in this is 3. Okay, so we must frame some rule which will say that the number of significant figures in this is only 3 over here. Like, we must not count this 0 as significant. So we must have a set of rules, okay, regarding the significant figures, and mainly that rule will be regarding 0, that when 0 would be counted as significant and when 0 will not be counted as significant. So let's understand about those rules. Okay, so rules regarding the significant figures. So the first rule is very obvious, that all non-zero digits are significant. Let's say, for example, somebody is reporting 23.58 kg, something like that. So it is clear all these are zeros are non-zero. So number of significant figures is basically 4. Okay, clearly. Okay, and the second rule, let's understand, like all zeros between two non-zero digits are significant. Say, for example, 20.08 we are writing. So these two zeros are between two non-zero digits, so these must be counted as significant. So here also number of significant figure is 4. 1 2 3 4. Right. The third rule here is, you can say, if a number is less than 1, let's say, if the number is less than 1, either it is a 0.01200, something like this. Okay, so in that case, we are in always a dilemma, that whether these two zero we should count it as significant or not, these two zeros should count it as significant or not. So the rule here is, okay, if we are having, okay, a number which is less than 1, and let's say, like these are two non-zero digits, so the zero left of it means this zero, or before that, these two zeros will be insignificant or insignificant, and these would be insignificant, you can say, and these two zeros would be, you should realize, that is significant. Okay, so that is the rule. So when you will be counting the number of significant figures here, this is significant 1 2 3 and 4. So the number of significant figures here would be nothing but 4. And the fourth rule I must tell you is about, okay, like if we are having a number without decimal, for example 2500, and we are having some trailing zeros. So trailing zeros are insignificant, you should realize. So only two significant figures we will be having in this. Okay, so number of significant figures in this is nothing but equal to 2. All these rules we are simply framing because we need to have same number of significant figures. If we change the units also, like you saw in the previous example, okay, even after framing these many rules, some ambiguity is still left. Okay, let's see, for example, one ambiguity I am talking about, let's say I have measured some mass, okay, and it is say 3.800 kg. Okay, obviously the measurement is quite precise over here, and we have number of significant figures as 4. But try to understand, if we represent it in gram, let's say in gram it would be 3800 gram, and according to this rule, so the number of significant figures, in just by converting units we have reduced, so significant figures will be equal to 2. So that cannot be the case. Okay, so this is basically ambiguity. So in order to remove this ambiguity, measured values are represented in terms of scientific notation. Let's say, for example, any value, any measured value, okay, will be represented in terms of a into 10 to the power b, and this is nothing but scientific notation of measured values, where you should realize that a would be some number, okay, that would be less than 10 and greater than 1, and b is any positive or negative exponent of 10 that you are understanding. So if we are using the scientific notation, for example, in this case only, so for example in kgs we are to write, so that would be 3.800 into 10 to the power 0 you can write. Okay, like see, I have represented this in terms of a number. This 3.800 is a number which is less than 1, less than 10 and greater than 1. If we want to represent it in gram, so that would be simply 3.800 into 10 to the power 3 gram, that is kg. And for example, in other units also you can represent, let's for example 3.800 into 10 to the power let's say 4 milligram, you can, or 10 to the power 5 centigram you can write, something like that. Okay, so yeah, like in that case, when you are looking for the number of significant figures, so you have to look only at the number of significant figures in a. So one rule will be sufficient to look for the number of significant figure in this. So this is a number with decimal, so all the trailing digits will be counted as significant. So there is a lot to talk about this thing, and we will continue from here in the next class. And in the next class we will be looking at rules for arithmetic operation involving measured value, and we will talk about absolute error, relative error, and percentage error in the measurement, and we will also look into the combination of error. And finally we will talk about vernier caliper and screw gauge. Okay, so today our time is up, so we have to stop. Okay, and